Molecular geometry is the three-dimensional arrangement of the atoms that constitute a molecule. It determines several properties of a substance, including its reactivity, polarity, phase of matter, color, magnetism, and biological activity. The angles between bonds that an atom forms depend only weakly on the rest of molecule, i.e., they can be understood as approximately local and hence transferable properties. Determination. The molecular geometry can be determined by various spectroscopic methods and diffraction methods. IR, microwave and Raman spectroscopy can give information about the molecule geometry from the details of the vibrational and rotational absorbance detected by these techniques. X-ray crystallography, neutron diffraction and electron diffraction can give molecular structure for crystalline solids based on the distance between nuclei and concentration of electron density. Gas electron diffraction can be used for small molecules in the gas phase. NMR and FRET methods can be used to determine complementary information including relative distances, dihedral angles, and connectivity. Molecular geometries are best determined at low temperature because at high temperatures the molecular structure is averaged over more accessible geometries. Larger molecules often exist in multiple stable geometries that are close in energy on the potential energy surface. Geometries can also be computed by ab initio quantum chemistry methods to high accuracy. The molecular geometry can be different as a solid in solution and as a gas. The position of each atom is determined by the nature of the chemical bonds by which it is connected to its neighboring atoms. The molecular geometry can be described by the positions of these atoms in space, evoking bond lengths of two joined atoms, bond angles of three connected atoms, and torsion angles of three consecutive bonds. Isomers. Isomers are types of molecules that share a chemical formula but have different geometries, resulting in very different properties. A pure substance is composed of only one type of isomer of a molecule. Structural isomers have the same chemical formula but different physical arrangements, often forming alternate molecular geometries with very different properties. The atoms are not bonded together in the same orders. Functional isomers are special kinds of structural isomers, where certain groups of atoms exhibit a special kind of behavior, such as an ether or an alcohol. Stereoisomers may have many similar physiochemical properties and at the same time very different biochemical activities. This is because they exhibit a handedness that is commonly found in living systems. One manifestation of this chirality or handedness is that they have the ability to rotate polarized light in different directions. Protein folding concerns the complex geometries and different isomers that proteins can take. Types of molecular structure. A bond angle is the geometric angle between two adjacent bonds. Some common shapes of simple molecules include linear. In a linear model, atoms are connected in a straight line. The bond angles are set at 180 degrees. For example, carbon dioxide and nitric oxide have a linear molecular shape. Trigonal planar. Molecules with the trigonal planar shape are somewhat triangular and in one plane. Consequently, the bond angles are set at 120 degrees. For example, boron trifluoride. Bent or angular molecules have a nonlinear shape. For example, water, which has an angle of about 105 degrees. A water molecule has two pairs of bonded electrons and two unshared lone pairs. Tetrahedral. Tetra signifies four, and hedral relates to a face of a solid, so tetrahedral literally means having four faces. This shape is found when there are four bonds all on one central atom, with no extra unshared electron pairs. In accordance with the VSEPR, the bond angles between the electron bonds are arccos equals 109.47 degrees. For example, methane is a tetrahedral molecule. Octahedral, octa signifies 8, and hedral relates to a face of a solid, so octahedral means having 8 faces. The bond angle is 90 degrees. For example, sulfur hexafluoride is an octahedral molecule. Trigonal pyramidal. A trigonal pyramidal molecule has a pyramid-like shape with a triangular base, unlike the linear and trigonal planar shapes but similar to the tetrahedral orientation. Pyramidal shapes require 3 dimensions in order to fully separate the electrons. Here, there are only 3 pairs of bonded electrons, leaving one unshared lone pair. Lone pair, bond pair repulsions change the bond angle from the tetrahedral angle to a slightly lower value. For example, ammonia. VSEPR table. The bond angles in the table below are ideal angles from the simple VSEPR theory, followed by the actual angle for the example given in the following column where this differs. For many cases, such as trigonal pyramidal and bent, the actual angle for the example differs from the ideal angle, but all examples differ by different amounts. For example, the angle in H2S differs from the tetrahedral angle by much more than the angle for H2O does. 3D representations. Line a stick. Atomic nuclei are not represented, just the bonds as sticks or lines. As in 2D molecular structures of this type, atoms are implied at each vertex. Electron density plot shows the electron density determined either crystallographically or using quantum mechanics rather than distinct atoms or bonds. Ball and stick. Atomic nuclei are represented by spheres and the bonds as sticks. Space-filling models as CPK models. The molecule is represented by overlapping spheres representing the atoms. Cartoon, a representation used for proteins where loops, beta sheets, alpha helices are represented diagrammatically and no atoms or bonds are represented explicitly, just the protein backbone as a smooth pipe. The greater the amount of lone pairs contained in a molecule, the smaller the angles between the atoms of that molecule. The VSEPR theory predicts that lone pairs repel each other, thus pushing the different atoms away from them.